Welcome all to our second session today of Hosting Earth, and it is entitled Fish Live in Water. It's a performed lecture by our own Sheila Gallagher, artist and professor here in Studio Art and mover and shaker in so many cultural events that happen in this university and elsewhere, and also a founding co-director of Guestbook from the beginning, and a great collaborator again and again. Melissa Fitzpatrick, who will be moderating this session, will give a proper introduction to Sheila and John Manderson, our visiting oceanographer and marine biologist, in a moment. But I just want to say a quick word of special thanks to the Sheila Institute for Integrated Science here at Boston College, and Laura Steinberg, our new director of this new initiative, who has very kindly sponsored this event. This morning I thanked all of our 10 sponsors for the overall 2 days, but for this particular event, Sheila Institute are our designated sponsors, so we're very grateful to them and to you, Laura. Finally, just a quick word on Melissa Fitzpatrick, Director of Communications of Guestbook, also more or less there from the beginning, and who in this very room, indeed, on March 18th, moderated our first event of our Hosting Earth series. And some of you will have seen the film video of that Poetics of the Earth event this morning. So just to say that Melissa teaches here at Boston College in environmental ethics in the business school, and is shortly moving off, alas for us, lucky for LMU, in Los Angeles to a tenure full-time teaching track over there. So we're delighted to have her here for her last Guestbook service, but I'm sure she'll be coming and going. Anyway, over to you. And I should mention also that Melissa is the co-author of the recent book published by Routledge, Radical Hospitality from Thought to Action, which is sort of the philosophical manifesto of the Guestbook project. Over to you, Melissa. Thank you.
Thank you. Thank you so much for being here, everyone.
And before, one last thing. I just want to say a special word of welcome to our guest of honor, Mary Robinson.
Yay.
Who flew something like 15 hours yesterday from Lake Como to Milan to Frankfurt to Logan Airport to Boston College to be here, and she's flying back to Ireland tomorrow, so we're very, very grateful to have her here for this special celebration of Earth Day and for the raising of consciousness about climate justice. But that's for this afternoon, when I will, at 4 o'clock after this, we'll have sort of half an hour to get from here down to Heights, and I'll do a proper introduction at that point, and we will hear what Mary has to say. Very good.
Thank you. Thank you so much for being here. It's funny, Anne told me what I started the March 18th panel with was thanking everyone for sacrificing being indoors when it's so beautiful and sunny outside. The same thing holds today. Thank you for being in here. So I'll start by briefly introducing our performing lecturers. So Sheila Gallagher is an artist, curator, and professor here at Boston College. And our innovative interdisciplinary work explores perception, belief, and different modes of representation. She works in and through a variety of media: video, smoke, drawing, live animation, light projections, live flowers, and plastic trash. Her flower installations and plastic landscapes, innovatively working with melted plastics, are among my favorites, which is why I bring it up. An interesting way to upcycle. Sheila's work has been showcased all over the United States, including at the ICA and MFA here in Boston, and at the Dodge Gallery in New York City, and also abroad, including at the Moving Image Festival in London. She's the co-director of the Becker Archive, the largest private collection of Civil War drawings, and she's also our co-director at Guestbook Project. Richard alluded to this. Sheila is a true visionary and such a generous and compassionate human being, devoted to art and the imagination, fueling community healing empathy and exchange, understanding and transformation. So we're so grateful to have Sheila performing here with us today. And we also have John Manderson. He's an oceanographer and consultant at OpenOcean Research, where he oversees research projects and partnerships aiming at the support of sustainable marine resource use. Recent projects have included membership in the 2021 Research Track Population Assessment Working Group for Northern Shortfin Squid and the collaborative development of the Fishery Knowledge Trust with the Responsible Offshore Development Alliance and Consider, Inc. Prior to forming OpenOcean Research, Dr. Manderson worked for more than 20 years at the U.S. National Oceanographic and Atmospheric Administration, NOAA, as we all know it, as a marine ecosystem scientist, research fisheries oceanographer, and expert in industry science collaborative research. All of John's projects are in response to the rapid warming of the Earth's atmosphere and oceans and abrupt ecological changes that can be quite difficult to understand and involve transdisciplinary collaboration with experts from the fishing industry, the government, academia, environmental NGOs, working to design effective solutions to complex problems. So we are so lucky to have John performing with us here today. Thank you.
Before we make the room completely dark, I wanted to say first thank you, Melissa, with the nicest introduction anybody's ever given to me. It makes me want to cry. And I look out at this audience and I see my students, I see my colleagues, I see Larry Robinson, I see Laura Steinberg, who so generously supported this, the Schiller Institute supported this program. I want to do a shout out to my students in Advanced Mixed Media who made this quilt of an endangered marine life for this talk and this for Earth Day and hosting the Earth Conference. And thank you for taking the sunny day to be here, and they really helped me put all this together this morning, with all the little bits and pieces, carrying them. And to John, who I've known for over probably 30 years, and I've loved, the reason we're doing this is because over that 30-year period, I've listened to him explain complex science, and especially fisheries, to me over the dinner table, and I think, this needs to get out. This can't just stay with me at the dinner table. And he really is one of the world's most, one of the world's experts on population assessment, which is so key to understanding how we can live with our oceans, and is, as Melissa said, a pioneer in terms of collaborating with industry, academia, science, and government. So thank you, and now we're going to turn off all the lights.
Guest host or castaway. In the voyage of the Pequod in Melville's Moby Dick, Pip, the black cabin boy, entertains the crew by playing his star-belled tambourine. Pip is the keeper of time. Otherwise, Pip is not very useful in whaling operations. Alongside the doughboy, he serves as a shipkeeper who tends to the Pequod while the rest of the crew man whaleboats and pursue whales. Occasionally, a member of a whaleboat crew is injured and a shipkeeper has to fill in. Pip substitutes in for an oarsman with a sprained wrist on a whaleboat commanded by Stubb, the second mate on the Pequod, a happy-go-lucky, successful hunter of whales. When Tashtigo, the Martha's Vineyard Indian, successfully harpoons a whale and it beats its tail to make its first run, Pip jumps, becomes tangled in the harpoon line, and is dragged overboard. Stubb sees all this and reluctantly orders Tashtigo to cut the line and free Pip alongside the whale. They pull Pip back into the whaleboat, and after the crew is through cursing him, Stubb advises, "Stick to the boat, Pip, or by the Lord, I won't pick you up if you jump. Mind that. We can't afford to lose whales by the likes of you. A whale would sell for 30 times what you would, Pip." Pip must substitute in again for the injured oarsman. And when the next whale responds in panic to Tashtigo's harpoon hitting home, Pip jumps again from the whaleboat. This time, Pip is not tangled in the line, and the whaleboat hurtles off, hitched to the fleeing whale. Pip is left a castaway to contemplate his aloneness in the expanding horizon and inky depths of an immense and heartless ocean. The ocean's liquid buoys Pip up, but his soul descends, which is to say his spiritual imagination descends to the depths, where the strange shapes of the unwarped primal world glided to and fro before his passive eyes. And Pip saw the multitudinous, God omnipresent coral insects that out of the firmament of the waters heaves the colossal orbs. He saw God's foot upon the treadle of the loom and spoke it, and therefore his shipmates called him mad. So man's insanity is heaven's sense, and wandering from all mortal reason, man comes at last to the celestial thought, which to reason is absurd and frantic, and weal or woe feels then uncompromised and indifferent as is God. What is Pip in the ocean he has found himself in after his revelation? Can either Pip or the ocean be considered guest or host? While the ocean in this context could be considered a lord of strangers, it can't know anything about welcoming and the ties of hospitality that bind guest and host. Pip is in fact an accidental guest, a chance comer, a stranger, a guest in the Old English sense. But being a guest implies for both guest and host the ability to return home somewhere else so as not to wear out any welcomes. No, at least at first, Pip is just a castaway. But after his revelation, he becomes something else. Some of Pip's shipmates think he's mad, but his madness comes from being shamanized by a revelation about the true state of nature. Pip is no longer a lowly shipkeeper who keeps time with his tambourine to entertain the Pequot's crew. Pip's revelation has shattered time, and he becomes the high priest who officiates the mock funeral of Queequeg, the South Sea cannibal chieftain. Harpooner. Ahab recognizes Pip's new mysterious and authentic powers, and in need of them, holds him close during the final few days of the pursuit of the white whale. It seems to me Pip's story and his experience as a castaway is relevant at levels from profane to sacred to the human problem of finding a way to live sustainably on the earth, whose carrying capacity for humans we seem to have reached and may well have exceeded. The Castaway chapter highlights particularly well the problems underlying the sustainable human use of ocean resources, which are just an extreme, exaggerated example of problems we face and the possible solutions we might employ to sustain ourselves in all the other ecosystems of the biosphere. Living in a liquid is different from living in a gas. If we focus first on the profane material world, which is what scientists do, Pip's story elucidates something important and true about the limits of human observation in the oceans and the nature of the ocean itself. First, after Pip falls overboard, he finds himself suspended at the surface of an immense and heartless ocean. Note, Pip is suspended in a liquid, not the gas of the atmosphere or the solid dry land. The density and viscosity of the liquid result in buoyancy forces that allow him to defy the laws of gravity and remain at the surface of the liquid in contact with the Earth's atmosphere where there is air to breathe. Pip's body is left floating at the tropical ocean's surface on a windless and cloudless day. The sun is bright, but light is extinguished 100,000 times faster in the liquid of the ocean than in the gas of the atmosphere, and is completely extinguished at a depth of about 600 feet, while the seabed may be 12,000 feet below him. Pip's body and his senses can't be carried down alive to explore the wondrous depths. Only his soul can be. Pip is a human observer. Most of the ocean is impenetrable to his senses, including sight, our far-field sensory modality. Pip's voyage into the depths of the inhospitable ocean can only be imaginative. The constraints imposed by his physiology and senses define an exceptionally limited observation window through which he can gather only fragmented glimpses of the true state of the ocean's nature. Despite recent developments of remarkable tools for measuring and simulating the physical and biological properties of the ocean, we are still, even now, quite blind to many truths about the nature of the oceans. Just like Pip, we are terrestrial organisms, and thus the oceans, where life's media is a liquid, are opaque to us, not transparent. We still rely on imagination to understand the ocean's properties and processes. Again, the ocean is a good example ecosystem because its extreme properties force us to wrestle with important truths about our nature and all the ecosystems we inhabit. Natural ecosystems are complex, and neither their structures or their dynamics are transparent. All ecosystems, even terrestrial ones, are opaque to human observers. Nevertheless, if we are careful to think about our observation limits and to fill gaps in our knowledge with hypotheses based on first principles of biology and physics, instead of analogies to our experience as warm-blooded, air-breathing creatures living along the interface between land and a transparent atmosphere, we can make inferences about the nature of the oceans and what might be different about living in a liquid instead of a gas. Life's media in the ocean is matter in a different physical state. The ocean's liquid is 850 times more dense and 60 times more resistant to stretching than the air in the atmosphere. Pip sinks very slowly because the density of his tissues is nearly the same as the density of the ocean's liquid. Resistance to stretching is viscosity, and the high viscosity of seawater means the drag rather than gravity is the dominant force controlling the movements of animals and other particles. Except for things attached to the seabed, everything in the ocean, including Pip, drifts downstream. Most marine habitats are not fixed in geographic space, but occur in hydrographic space. They are dynamic in both time and space, and more or less forever on the move. There is no shortage of water in the ocean, and the concentration of salts is close to the concentrations of solutes in the tissues of organisms. Maintaining the balance of water and salt required by cells for metabolism is relatively easy in the ocean compared with land, where the atmosphere is dry and devoid of salts. On the other hand, the rate of heat transfer in the ocean's liquid is hundreds of times faster than in air, and the metabolic cost of maintaining body temperature 1 degree higher than the external environment is more than 3,000 times more expensive than it is on land. The oxygen required to support the metabolic cost of warm-bloodedness is also scarce in the ocean. So most water-breathing organisms are cold-blooded. The activities, physiologies, and metabolisms of marine organisms are tightly coupled to the ocean's liquid, while many of these characteristics for terrestrial organisms are decoupled from the atmosphere. This is why the impacts of warming on a global scale on marine organisms appears to be occurring much faster than it is for terrestrial organisms. Processes supporting food webs in the ocean are also profoundly different. Viscosity is important in the ocean, but gravity operates too. Pip still sinks. As materials, including nutrients, drift downstream, they sink slowly beneath well-lit surface waters where plants can photosynthesize them to create carbohydrates and sugars and the free oxygen upon which all food webs directly or indirectly depend. The means of primary plant production are the forces that can stir the ocean, mix up and concentrate nutrients in well-lit surface waters where the plants can take them up to complete photosynthesis. The stirring forces of the ocean include tides produced by the motions of planets, the Earth, Moon, and Sun, currents driven by winds and rains produced by the Earth's turbulent atmosphere. Humans can't assist in tilling and fertilizing the oceans. We don't control the planetary and atmospheric forces driving the means of production of ecosystem production in the sea. Pip's insight into the sublime nature of the ocean, its wild immensity and indifference to humans, is consistent with our scientific insights into the fundamental nature of the ocean and the forces driving the dynamics of its ecosystems. Thinking of ourselves as hosts of the ocean misses the mark. Humans don't manage ecosystems. We manage our own activities in ocean ecosystems that we don't control and barely understand because they are opaque to us. This is true of all ecosystems in the biosphere. The ocean is just an extreme case. If we can't host the oceans, then can we think of ourselves as guests? The uniquely different adaptations of marine and terrestrial organisms are solutions to the identical problem of maintaining metabolism in either a liquid or a gas. Ultimately, all of life processes, from the normal functioning of cells through the dynamics of populations and communities, are fueled by the metabolic process of respiration, which requires some sort of fuel, complex organic molecules that can be converted to forms of energy useful for doing biological work. Life everywhere continues by killing and eating. There is no exception. In this, humans are unexceptional. This is our nature. It is important to recognize that seafood is an important source of fuel for humans. Fish and other seafoods are nutritionally important to 42% of humans on the planet and the sole source of protein for 16%. At noon last Tuesday, there were approximately 7,900,000,000 people on the planet who require about 2,000 calories per day. The human population required 17.6 trillion calories last Tuesday. About 3 billion people depended upon seafood for nutrition, and 1.3 billion of these depended on seafood as their sole source of protein. The population reliant on fish is not inhabiting wealthy nations. Most live in developing nations. For example, a large amount of the Atlantic mackerel harvested on the U.S. East Coast is shipped frozen to cities in North Africa. There it is thawed out, salted, and sold in markets of cities like Cairo. Buyers carry salted mackerel back to villages where they smoke the fish and sell it again. From there, smoked mackerel is transported by foot into rural areas that lack any refrigeration. Most of the people that eat fish live at subsistence levels without any modern conveniences. Fish matter to humans, and it is important to be mindful of the trade-offs of meeting human metabolic imperatives using different food sources. I have a close friend named Bill Bright, who owns a large mackerel squid trawler that harvested 5 million pounds of squid during the summer of 2018. The fishery is clean. He catches the squid with a net towed close to the bottom, but not on it, and the catch of other species or bycatch is low. If you do the math, Bill's 5 million pounds of squid contain 2 billion calories. 2 billion calories of wheat is 23,760 bushels, and an acre of land yields about 48 bushels. So about 500 acres of land needs to be cultivated to grow the energy equivalent of my friend Bill's catch of squid in 2018. The wheat production requires demolishing diverse habitats and at least displacing organisms that use them in a natural terrestrial ecosystem, and then maintaining a wheat monoculture by human force of tilling, watering, fertilizing, and applying pesticides on an annual basis. Bill caught 2 billion calories of squid along the outer edge of the continental shelf, where the productivity is supported by the stirring of the ocean by winds and tides, by the Gulf Stream, its rings and its streamers. These are planetary and atmospheric forces we don't control. The ocean does it itself. The upshot of all this is that humans depend for subsistence on food produced by weakly bounded, complex ecosystems driven by forces we don't control and barely understand. We aren't hosts to the oceans because we don't control the forces controlling the means of production. The ocean isn't much of a host to us since it can't know a thing about hospitality. Pip knows it's an uncompromised and indifferent God. We aren't guests because we cannot leave and go elsewhere. We depend upon it. Our unexceptional metabolic imperative means we are inextricably embedded in the Earth's systems. Our dependency on them is not negotiable. I first met Bill at a workshop on Long Island where scientists and fishermen discussed the problem of understanding and estimating the numbers of squid in the sea. In the hallway during a break, we had an excited conversation about the Gulf Stream, its rings and its streamers, and the tools we now have to visualize the ocean. We talked about how we could combine our knowledge and tools to better understand how tunas select habitats in the sea. Eventually, we broke off the conversation to get ready for the next session that was soon to start. Bill turned and walked away. Then he turned back, smiled, and said, "I need regulating." That's true. He does need regulating. And we need him to be regulated because Bill is our surrogate hunter who allows us to pick out our fish from the assortment in a freezer case and have it passed to us bloodless, wrapped neatly in wax paper. The scientific basis of regulating Bill needs to be accurate and sound for the ocean, for Bill, and for all the rest of us. How many fish are in the sea? The size and productivity of fish populations and the rates at which they are estimated are estimated in population assessments. It's a hard problem. Fish population assessments are done by building 2-part statistical machines. The first part is a mathematical model describing the natural and human processes affecting fish population size and how they change over time. In the process model, fish are added to the population through reproduction. They can also be added by immigration. Fish are subtracted by dying from natural causes or fishing. They are also lost when they emigrate. To make the model solvable, we ignore nuisance processes by making assumptions. For example, we usually ignore both immigration and emigration. We also assume that many processes exhibit stationarity. They vary randomly without any systematic directional trend. This is a critical concept. Assuming stationarity means we can account for a process by just introducing some random noise. And we can use the patterns of the past to predict the possible future states of nature. In this case, by assuming stationarity, we assume the past is prologue. The second part of the statistical machine is an observation model of characteristics of the fish population and the fishing process we can measure that directly or indirectly correspond to the process variables. This is the stuff like the size, age, reproductive condition of fish caught on scientific surveys. We also measure the mass of fish that fishermen catch, as well as the size and age of some of the catch. We make assumptions about the observations too. The fishery catch is known without error. There are simple relationships between the true state of the population as a whole and the abundance of other characteristics of fish measured in surveys in the fishery. We also apply the stationarity assumptions to observations in order to simplify the problem. For example, we assume that fish aren't changing their distribution within our observation window in a way that confounds our interpretations of measurements of indicators of population condition. We cannot directly measure many of the processes that we need to know to estimate what can be caught, including population size, reproductive rate, and mortality as a proportion of population size. In some cases, we make up some swag, or scientific wild-ass guesses. For instance, natural mortality is often fixed at a number like 2.2 because it is nearly impossible to estimate. And we usually assume that natural mortality is also stationary. It varies at random, but without any trend. This is convenient because it allows us to assume that fishing causes all changes in fish depths over time. We then couple together our process and observation models with all their assumptions using some fancy math to arrive at a solution producing estimates of the variables that we need to know. Fish population assessments apply an operations research and management science approach to figuring out the number of fish we can harvest from the sea. Operations research was developed by the British Royal Air Force to route aircraft bombing runs during the Second World War. After the war, it was taken up by others like the Rand Corporation that applied the method to tame society's problems and to develop sound public policy. OR proceeds in a logical sequence of steps. The first is to clearly understand the problem. The second is to make assumptions that limit its scope and allow the formulation of a model that's solvable. Next, you collect observations and measurements to inform the model and to evaluate, and you confront the model with data to produce a qualitative solution. You then validate the solution with additional data, and then use the solution to formulate and implement public policy. I had a yoga teacher who began every class with the question, do you want to be an example or a warning? I'm going to discuss the history of the Atlantic mackerel population assessment, which is a bit of both. First, we need to know a few details about the fish. Mackerel are very fast-swimming, schooling, cold water fish. They are an important global seafood product. The species occurs on both sides of the Atlantic. On the eastern side, they occur from North Africa and Spain as far north as the Barents Sea. In the western Atlantic, they occur from northern Newfoundland, as far as we know, as far south as Cape Hatteras in the mid-Atlantic. Mackerel have a complex life cycle, which includes eggs fertilized externally in the sea, tiny larvae that feed on even tinier crustaceans. Small juveniles and adults are carnivorous and feed on fish and crustaceans. All life stages live up in the water column, but each stage has unique habitat requirements that must be met if the fish is to survive and reproduce, a necessary precondition for population growth. Large juveniles and adults migrate from northern summer feeding grounds to southern overwintering areas. As they migrate north in the spring, they spawn on nursery grounds along the US and Canadian coasts. These are observations of mackerel abundance from a scientific bottom trawl survey conducted during the spring and fall. The survey samples stations randomly within geographic and depth zones on the continental shelf between Cape Hatteras and Canada. A small net is towed at about 400 stations on the bottom for about a mile at 3 knots. Average abundance in the survey catch is calculated, and this index is used to infer population trends. So this is average number of fish per tow per year. And what you can see in this data is that there's a big spike in survey catch around the 70s, which declines, and then, since about 1980, we've seen an increase, and that extends to about 2010. So their this bottom trawl index suggests that the population increased from 1960 through about 2010. And this box here is data that is used in the 1995 assessment, which I'm going to discuss in a slide or two. This is U.S. fishery. This is another part of the observation data. This is fishery catch from 1965 to 2015. The assessment used fishery catch to determine the scale of populations as well as fishery mortality. Catches were very high in the early 70s, and then they dropped off, after which time we had some cycling through about 2015. The important thing is this data was also used in the 1995 assessment. And the important thing to think about here is that we normally use fishery catch to scale population size. So if we use the surveys to tell us about the trend, whether it's up or down, and then we use the fishery catch to help figure out the population scale. So this is the result of the 1995 assessment. And this axis on the left is the weight of the mature females. This is the year, and then this is fishing mortality. And what you can see is, that there was a time when fishing mortality, and the model predicts that the fishing mortality was very high in the 70s. But then fishing mortality fell off, and by the end of the time period that dealt with in the assessment, about 96% of the fish are surviving. This shows the biomass of spawners, this blue line, and you can see at the end of the assessment, it's telling us there are about 2 million metric tons of mackerel in the sea. Now, this is science that's done for assessment. So what happened with this assessment is we developed some fishery policy. So in the early 90s, a fishing quota was set at 1 million metric tons. And Congress got wind of this assessment and formed a U.S. Trade Commission that fostered the development of a high-volume mackerel fishery in U.S. waters. It turned out is that as the fleet began to expand, the fishermen were catching only 1.4% of this quota. And the fishermen had been saying this for a while, that the scientists were creating paper fish. That the fish the model was producing weren't there. And the scientists, and you can actually read the documents, where it states, well, the fishermen actually don't, the problem isn't the abundance, it's that the fishermen can't find the fish. In 2000, the fishermen requested the Mid-Atlantic Fishery Management Council to exclude any new vessels from the fishery. And what the council came back and they said, well, we're not going to constrain the fishery. There is a foregone yield of fish in the water each year of about 100,000 pounds, and we think that the fishery can be increased substantially. Between 2000 and 2017, the fishery never caught more than about 20% of the catch. The status of the assessments became increasingly uncertain, and the status of the population became unknown. This is this is a plot of the 1995 assessment on top of a 2018 assessment that we were involved in. And it allows us to look to see what our new results tell us about that old assessment. And so the solid line is the information coming out of the 2018 assessment. The broken line is the 1995 assessment. And what the 2018 assessment told us is that, and remember, we built public policy on this, is that the assessment overestimated the amount of spawners in the ocean by 17 times and underestimated the fishing mortality for 17 times. Now, it's important to realize that this is not a fault of fishermen. This is a failure of fisheries governance. And it's a failure in the science process and a failure also, I think, of policymakers not to recognize the difficulties of actually trying to estimate the number of fish in the sea. Now, why do we think the 2018 assessment is any better? For one thing, we formed the Atlantic Mackerel Population Ecology and Fishery Expert Working Group 3 years ahead of the beginning of the 2018 assessment. The work group included experts from a diversity of relevant disciplines and institutions, including expert fishermen. The formation of the working group was an acknowledgement that the mackerel fishery system was opaque and that the problems were poorly understood. The working group produced a kaleidoscope of different perspectives, creating synergies of expertise and ignorance that broadened the observation window. And what we began to do was to try to wrestle with the complexity of the system. And so this is actually a simplified concept map of the system in which we explicitly tried to integrate both the wild and human ecologies of the socio-ecological system. Along with ecological processes that we typically think about, we considered the impacts of economics and including, as well as global geopolitics on fishery catch. We also thought a little bit about sociocultural forcing, which includes feedbacks of human politics and cultural bias through the management system into the development of regulations and in the way they feed back into the system. We discovered that a number of the key assumptions of the 2019 assessment were wrong. The first one had to do with our interpretation of what the trawl survey meant. Now, what was applied was the assumption that if you take the mean abundance from this survey and you calculate that's an indication of how big the population is. And that works for a lot of different kinds of fish. The problem is it doesn't work for schooling pelagic fish. So if we think, and this happens with a lot of fish, that schooling changes in a very complex way with population size in small pelagics, including mackerel. And what tends to happen is when the population is small, the animals form very small schools that are dispersed throughout the seascape. When the population is big, they concentrate into super schools, which can be as big as 20 miles long. And those super schools tend to concentrate in specific geographic areas. The other thing that we need to know is that the mackerel burst swimming speeds are about 6.5 knots. And that is super fast, and it's super fast compared to the survey, which is only sampling the bottom at 3 knots. So if doing some spatial analysis on this data, what it looks like is happening is the survey is measuring the number of schools, but not the volume of the schools, or the number of fish per unit volume. And in order to understand how big the population is, you need to know all those 3 things. You need to know school volumes, the number of fish per volume, and the number of schools. So because it's only measuring the number of schools, and the population schools do this, it means your index is telling you exactly the opposite of what you think it is. So it's actually low when the population is big and the animals get concentrated in super schools, and the index is high when the population is small and the animals form many schools that are dispersed out. So that's part of the part of the problem with the 2019 assessment has to do with the assumption of what the observations mean. So this is another part of our observations, except that, and this is amazingly, typically we don't go back in history like this. Normally we go, all right, we're only going to think about data from here and here to here, and we're just not going to fuss with all the rest. But this is the catches of mackerel in U.S. waters since 1800, and there are a number of interesting things about it. You know, the first thing is that there's a ramp up in around 2015, and this is the response to what people often talk about as the year without a summer. There was a volcano called Tambora that blew up in I think 1814 or 15, and it sent clouds of ash into the atmosphere, so that the next year, in 2015, there were hard frosts from throughout New England as far south as Cape May in June, and widespread crop failures. And it turned out at the time there was a fair mackerel were available in the water, and that mackerel in New England became a very important subsistence food source during that period. And they maintained pretty high catches during the 1800s until about 1880, in this period called the Great Heat. Right, and the Great Heat was a period of when there was a climate cycle and there was relatively warm period. Now the first thing that it's telling us is there's probably some climate signal in this animal, and we have to be very careful about when we apply the stationarity assumption. So catches were relatively low throughout the 1900s, and then all of a sudden what you see is this massive spike in the 70s. Now in 1953, Khrushchev implemented a program where he would turn the Soviet Union into a global fishing power, and it was in response to the famines in Russia and other places in the Soviet bloc. And these catches, they developed a remarkable fishing operation of massive power, and I think that the goal was to provide 23% of the protein required by Soviets with fish. And 10% of that content was supposed to come from the Northwest Atlantic. And in fact, it did. So you ended up with this massive spike in catches. And then we start implementing federal fisheries regulation. And then in addition to that, we set up the EEZ. and we see catches like this. Now when we did the 1995 assessment was done, this 1970s catch was included in the observations used to scale the data, scale the result. But if you look at you consider the whole height of tire history, and I think this is amazing, is that the maximum catch looks like it's here, and it's the same when they're fishing with sailing vessels as it is when they're fishing with large modern trawlers. So the 95 assessment said that somehow this was sustainable, and that spike was supported by population productivity. Whereas if you looked at the history and really got interested in the history of this animal, the sustainability level was here, right? So the mistakes that were made had to do with the assumptions that we made. Now the other thing that is interesting about this animal is that a lot of this information, a lot of these things we discovered by working directly with fishermen. And there are things that fishermen know that scientists don't know, because they couldn't possibly afford to spend the time on the water that fishermen do. And fishermen sample very differently. They chase fish as opposed to sample fish, but using stratified, random scientific designs. So what we were interested in the assessment was trying to understand distribution shifts in the animals. And these are plots that were built based on the fishery knowledge of the changes in migration over time. And what the fishermen discussed was that before 1990, it looked like there were actually 3 separate migrations of fish down from the Gulf of Maine into the mid-Atlantic bight during the spring and summer. There was an inshore run of fish here that was large fish that ran up and down the coast. They arrived early, and then but they swam up and down close to the beach. There was another group of fish, of smaller fish, that migrated down mid-shelf, and then there's an offshore group that migrated along the continental shelf. By 2000, that inshore group of fish was gone, according to fishermen. And after 2000, what we saw was that this group of middle fish no longer extended south of about New York City in the Hudson Shelf Valley. Now, it wouldn't have been possible to know this without working with fishermen. Now, this is some science that we did associated with it, and what it shows is the change in the distribution of adult and mature and immature mackerel in the system, and the rate at which it's moving northeast with what we believe is changes in climate. What you can see is they're moving at about 7 kilometers per year. And our original hypothesis, and this is consistent with what many scientists think, is that this was probably due to a change in adult thermal habitat. So you would think that the distribution of animals would change at the same rate as the distribution of habitat. But what we find is the red line is the shift in habitat. And what we can see is that's also moving northeast, but it's moving northeast at about half the rate. So that doesn't explain the problem. But what does explain the problem, probably, are changes in larval catch density. So this is the catch of newly born mackerel in the mid-Atlantic region from 2000 to 2004 to 2006 until about 2011. And what you can see is there's a massive decrease in the abundance of larval mackerel. And what we think has happened is that the larval mackerel need copepods like this, little bugs like this, in order to support their growth. And these are very fatty cold water bugs, but these animals disappeared from the mid-Atlantic during the 2000s. And if mackerel don't have the available food supply at the right size, what they do is they turn around and eat each other. They become cannibalistic. And the nursery habitat quality then evaporates very quickly. Now, there are a couple of things about that. One is that assumption that natural mortality, we know from this, is not stationary. That stationarity assumption doesn't work. The world is changing, and the past is not prologue. The other thing about it is that migration is genetically, it has a genetic component, and it doesn't take long to migrate a few times and have a failed reproduction to have that behavior no longer persist in the stock. You can get it back, but it's hard to get back. Fishing in a wicked world. Are we guests, hosts, or castaways, or something else? We're warm-blooded, air-breathing creatures inexplicably embedded within weakly bounded, complex, dynamic ecosystems we don't control. They are opaque to us, rapidly changing, and we depend on them for subsistence. We don't manage the oceans or any other ecosystems. We manage our own activities in them. We need to do this intelligently and carefully. We need to do it for the oceans, for my friend Bill, and for the rest of us. It's in our own self-interest. The history of the Atlantic mackerel fishery since 1950 is a warning about the consequences of failures of fisheries governance, specifically on the science side. From the late 1980s through the early 2000s, the mackerel assessments were inaccurate because of a shortage of brain power. There were and are plenty of brilliant people in fishery science. The failure was grounded in the application of the operations and research and management science approach and the worldview that lies at its foundation. When it comes to figuring out how many fish are in the sea, the OR is the wrong tool. Operations research works well on relatively simple, transparent systems we understand well enough to make simplifying assumptions required to formulate models that we can solve with data. The stationarity assumption is crucial. It allows us to substitute random noise for ecological and observation processes we know are important but don't really understand. We assume they don't change systematically over time. The past is prologue. The problem is that the past is no longer prologue because warming at a global scale is causing directional change in ecological processes, driving population dynamics, as well as our observations of them. In general, the stationarity assumption doesn't hold. In our example, mackerel are shifting northeast out from underneath our survey observation window. The nursery habitat quality declined after the 1980s, and the natural mortality, which we had assumed was stationary, increased over time. So the context of the problems of fisheries are rapidly changing, and every problem, even the old problems, are new ones, requiring new solutions that will always be provisional. This is probably true, particularly true, of applied science problems used to formulate effective public policy. If the policy has impact, the impacts change the context of the original problem, and the solution will eventually be wrong. These and a few other characteristics of socio-ecological fishery systems make them wicked problems. Wicked problems aren't evil, they're just seriously devious. And those who try to solve them, policymakers who try to solve them, sometimes end up facing some nasty consequences. One way we have begun to address the wicked applied science problems of fishery systems is to bring together diversities of experts in ecology, oceanography, the fishery, and social sciences willing to work together to rethink these problems. We have done this now for 2 assessments, other than just the, in addition to the mackerel assessment. I'm optimistic that we will be able to do it again. In each case, collisions of different perspectives created synergies of expertise and ignorance and allowed the group to gather all the fragmented glimpses together to make a much broader window of observation. Engaging expert fishermen has been crucial. Fishermen sustain their engagement in the realities of the ocean, the fish, and the fishery on a daily basis. This kind of engagement is not feasible for scientists. Fishermen have different and sometimes better tacit understanding of the realities of the system, from the schooling of fish to the impacts of global politics on fish markets. Many of the increases in assessment accuracy that we have achieved using this approach have involved the translation of the tacit knowledge of fishermen into explicit scientific knowledge that could be formally integrated into assessments. Some believe our engagement with fishermen in the assessment problem risk regulatory capture. Others find it valuable primarily because it gets buy-in from fishermen whose livelihoods will eventually be constrained by regulatory outcomes, while they dismiss the value of the knowledge of fishermen. But buy-in is just a collateral benefit of the improvements of science. Science is a tool for knowledge creation that's rooted in culture and worldview. At its foundation, operations research adopts a decidedly anthropocentric view of the relationship between man and nature. There is faith verging on hubris in the power of the human impact and intellect and technological progress. Human intellect and technology will permit us to mitigate our effects on nature and the biosphere, which we view as something other. I think this leads us now back to Pip, but a step or two away from the profane world of fish and physics. I've always been confused by the relationship between Pip and Ahab at the end of Moby Dick. Maybe Ahab identifies Pip's madness with his own, and out of compassion makes him his secret sharer during the final few days of the Pequot's voyage. But Ahab's vengeance doesn't seem to have any room for compassion in any other place in the book. Instead, I think Ahab recognized and coveted Pip's newfound power because he knew he would need it in his last battle with the white whale. Would Ahab have coveted Pip's power if it had just been the consequence of the internalization of the revelation of an uncompromised and indifferent God external to Pip? I don't think so. It seems to me that in the crisis caused by being left alone a castaway, suspended and defying gravity in the inky darkness, Pip became something else. I think he recognized deep in his own nature and in the nature of the ocean surrounding him the self-same identity. His power wasn't supernatural, it was infernatural. It wasn't actually new at all, but it had always been both internal and external to him at the same time. It was his true state of nature and the true state of nature of everything else. I think we all need Pip's new worldview, the recognition that nature is the center of man, just as it is for everything else. It's a necessity if we're going to better manage ourselves intelligently and carefully in a biosphere we don't control and are just barely beginning to understand. I think this worldview is a paradigm shift as important to us as now as Copernicus's revolution in the 16th century.
And to conclude, I think what is so exciting about this worldview is that it's an invitation for complex collaboration, for multiple intelligences, for humility and the ability to entertain uncertainty. So thank you for putting up with my uncertainty up here. And thank you for coming.
We'll go for it. Does anyone have any questions for our performers? Yeah, please.
I have a question. Do you have a similar data for herring?
Herring.
Yeah, and the same food chain, right? And if herring is protected, why isn't mackerel also protected?
Well, right now, after the 2018 assessment, the quotas were set at 4,000 metric tons, which is nothing. So the fishery is effectively shut down, and the fishery is shut down. Which is difficult for the people who are in the fishery, because we need to remember that there was the results of that '94 assessment that the government was giving people loans, including my friend Bill, to build large pelagic trawlers that are designed for herring and mackerel. And those fish were never there. And there's another complication to this. It's not, the role of climate in this is really important in both stocks, but it's very difficult to get a handle on, because it's not just affecting your observations. I mean, it's not just affecting the population, the processes. It's affecting your observations and teasing apart shifts in distribution and how they result in changes in abundance versus, and you may misinterpret as a change in population size or vice versa. It's a very, very, very difficult, hard problem. And it's a very hard problem that the science process as it's currently designed is not designed to handle. And the reason I say that is the science process, you write a grant, maybe you do it twice, so there's 2 years. So you identify a problem, you write a grant, you get the money, if you're smart, you do 2 years of data, 2 years of analysis, you write it up, that's 5 years, it gets published. How long does that take? It usually takes 6 months at best. And then it needs to be out, and then you're 5 years beyond the state of the universe when you identify the problem. Meanwhile, the ecosystem and all parts of it are there. So you can't be right. You actually can't be right. With a changing climate, you cannot be right given the way we do science right now. It's not possible. And I don't believe you can do it right unless you embed inside fishery science, that is, embed inside the fishery and do it in near real time. Then you might get accurate, maybe. But you're going to make mistakes, and you need to figure out, you need to get a lot of smart people in the room, including fishermen, and to understand their solutions are provisional, always. But I'm convinced that you can deal with the problem of sustainable fishing if you rethink the problem of how the governance is done. On this, and particularly, I'm an expert on the science side.
Now, at the end of our morning session, there was a general consensus that ecology and the struggle for climate justice needed to have recourse to the arts, various forms of the arts, and different examples we're taking. This afternoon, we've seen sort of the emphasis shift more to science, or at least art science. And what I'd like to ask you both is how you, John, coming from your scientific experience and research, and you, Sheila, coming from your artistic experience and research, found this coming together of art and science sort of mutually enhancing, mutually frustrating, mutually impossible, mutually creative. In other words, as I saw you both going there, one of the things was like left brain, right brain, the two different panels, the different projections, and the fascination, and maybe it's this uncertainty principle you were talking about, how do they connect? And there were resonances and so on. Clearly you were responding to the different shifts and paradigms and models that you were presenting there. And you, John, were taking at the beginning and at the end an example from literature. Pip's experience going down to the bottom of the ocean in Moby Dick. So it's just sort of a very punctual question today as to how the two of you performing in this way, planning it for some years, but actually putting it together in the last few days. What's going on that can help us?
I would say we talked about it for a few years.
We talked about it for years and years, right?
Then we planned it in a week.
I mean, it's been a completely harmonious and perfect collaboration. But I would say that part of what we're trying to do is actually embody, illustrate. I'm doing the live time. Like I'm kind of doing the science that's in the now. That is art in the now. He's showing you the charts, right? It's built on years and years of cumulative research. And the idea is that you kind of need, you do need both. And you do need to bring these multiple intelligences together. I mean, I think one of the things about John and his research is that it's absolutely dependent on multiple intelligences, multiple disciplines. But I'm the one who's like, we don't know all the answers. We'll never know all the answers. Like we cannot control nature on some level. I can't control the fish tank.
But you're also, I mean, I can't, science deals with the material world in a very analytical way. And, but it rests on a cultural foundation. And it rests on a foundation about, it's based on a human perspective on its relationship to the world. And it is a very simple, sort of silly example, but as an ecologist, you're trained to think, if you were trained in the 80s and stuff, you were trained to think of, well, I'm going to study a system, and I'm going to be the objective viewer, observer. I'm going to do an analysis, and I'm not really going to think about human impacts. So you start a research project in New Jersey on the Hudson Shelf, on the Hudson Raritan River estuary, and you're trying to ignore the fact that there are human impacts. It's insane. I mean, we're actually trained in an insane way. And I think that artists deal with the sublime and things that are beyond words, and they make references to whatever lies at the ground of our being, and that percolates up and informs our science and the stance that we take to addressing the problem. I think that's really required. I don't think you can sort of have. We have a lot of hubris scientists, and we think we can solve stuff, and we'll get some artificial intelligence and smart algorithms and all the data we could possibly collect and predict what the future will be, when the future's not going to be what the past was like. And it doesn't make us. That's not going to work. But there are, you can change your relationship to nature and think about it in a different way, and then, be somewhat humble and not have hubris and tell people there are a million metric tons, we'll give you loans and go get them. And then everybody now is beating up these people for having big paratrawlers, and they all want them out of the water, and they're getting vilified by the Nature Conservancy and FEW and stuff like that. Well, it wasn't their fault, right? It was a science problem. It was a science problem. It didn't, where scientists didn't recognize, that humans are embedded in this thing, and we don't know. We don't know enough. We're groping in the dark to get as good as it can get, and human beings are very ingenious at working together to find solutions. But the world is changing, and the solutions aren't going to be forever, and that's okay. But you need to be open open to other perspectives. And you really, it's hard in fisheries because, you know, fisheries scientists tend to be a very closed, arrogant lot. They don't want to listen, don't want to acknowledge the fact that fishermen might know something we don't know.
One more question? Yeah, Sheila?
I love the point you're making about timing in governance, right? That we don't have time to use old data for evolving issues, but of course there are cultural, I guess, perspectives of trust that go into the systems of error and authority that we use in crafting policy and in crafting scientific wisdom. So I'm thinking about the conversation this morning where we were discussing the absence of art in school and its continued decline in all of our social relationships, and I'm wondering from both of your perspectives if you think that, and in what form, reinfusing art into culture or artistic thinking, these different modalities of intelligences are one way, one path for us garnering a broader, scalable support for this new model of governance? What role does it play in the kind of thinking we need from scientists and fishermen and whatever coming together? Just more of like a material explanation of what you seeing that process looking like for policy, especially because certainly climate justice is not the only sphere in which our current mode of governance isn't working. We have other issues that are progressively evolving that need faster deliberation.
Well, I can say, I just speak from my small place of teaching art and being an artist. I notice in the classroom every year that my students have less and less tactile and material understanding of the universe. That sometimes I actually, for freshmen, I have to tell them how to hold a pencil, like you're not trying to wring a chicken's neck, right? And we actually like start like this, like loose, comfortable, flexible, but just to know like some hot glue gun is not going to hold together a car and a tree, right? And this, so the analogy I think is the fishermen who are out there, you know, in the material world, interacting with these beings. Careful observation, the number one thing. If art teaches you absolutely anything, it's the importance of careful observation, of just looking at what's in front of you without pre-assumptions, of learning to see, to be reflective about what you see. That's number one. The second is this realization that we live in, again, in a material universe, and to relate to that universe and each other as alive beings, right? That's in everything that has intrinsic properties, physical properties. And then the third would be this, no artist who's, what we teach in art class too is try, right? Like the beautiful try. Even if you're not going to get the perfect answer, the beautiful try and the effort of trying. And the willingness not to win, right? There's no competition, it's not competitive. It's like, you're a flower, you're a rose, you're a strawberry. Like you can't say which one is better, but this, again, what I talked about in the beginning is this willingness to risk failure sometimes and to entertain uncertainty, because if you know what it's going to look like before you go in, it's not going to be an artwork that holds anybody or your own attention.
Okay, let's give them another round of